Hello friends, welcome to a brand new tutorial series on active filters. In this tutorial we'll talk about the introduction to active filters and the fundamental concepts of active filters. Please understand, active filters are a newer technology than passive filters, and we'll talk about the limitations of passive filters first, so that we can appreciate why active filters were made in the first place. Now, if we talk about passive filters, their response was directly proportional to the characteristic impedance of the filter section. In other words, the characteristic impedance used to vary when the frequency used to vary within the pass band. So that was one big drawback. By the way, I highly recommend that you watch all the passive filter design tutorials on constant K type filters and M derived filters in order to better understand the active filters. And the second drawback that we had in passive filters was the load connections. So anything that we connect to the passive filter used to suffer from the transfer impedance of the filter section to the load section. So these two were the main drawbacks which were supposed to be taken care of by the active filters. And the first key point here, I write down the key points first. The first key point was the active filters. They did away with the bulky inductors. So bulky inductors were removed. So if you get a theoretical short answer type question on active filters, the first key point that you need to remember is that all the inductors were removed from the filter designing process, and we were left with resistors, capacitors, and op amps. And this brings us to the second key point, which says that it's cost efficient and compact, and losses were reduced. So if you can appreciate the fact that inductors being devices which have huge losses because of mutual induction, and electromagnetic losses were curbed in active filters, and they have much higher gain. Now please understand, the usage of operational amplifier makes it even more versatile. So at this point in time, I also recommend that you can watch the videos on the functioning of operational amplifiers if you wish to get a deeper insight into what is happening. And they were made compatible with ICs because the size has reduced considerably, so they were made compatible with ICs, and the Q factor has improved. So these were the key points. So you start off with discussing the limitations of constant K type and M derived filters, and you proceed on to the benefits of active filters. Now, if we talk about the theory behind active filters, we know that a filter is a two-port network device that filters the signal based upon the the frequency. So if we have a two-port network, again a two-port network, the we can always talk about two-port networks in terms of their transfer functions. So one key point here is the transfer function. So if I talk about the transfer function of a two-port network, which is in this case a filter, then it can be represented using h of s in frequency domain. So it is a polynomial of s in the numerator upon a polynomial of s in the denominator. Or another representation can be this. Now over here A can be thought of as the passband gain. So this A can be thought of as the passband gain, and S1 and S2, they are zeros, while SA and SP are the poles of the polynomial. So the order of the filter will be represented by the number of poles in the denominator of the transfer function. So this is one of the key point in designing an active filter. So if we were to say what's the order of the filter, we'd say that the order of the filter is referred to as the number of poles. So in this case, if the number of poles are 2, so we'll say it's a second order filter. And so as to say, this design will have a sharper cutoff frequency, because the transfer function will deteriorate or attenuate the frequencies in the stop band by an amount of 1 upon omega square. So this is the reason why we say that a second order filter is better than a first order filter, because it has sharper cutoff frequencies. And we can say that the fact is, a second order filter introduces a 1 upon omega square form at high frequencies, and or at the cutoff frequency the attenuation is much sharper, because it is omega square in the denominator. Now once we know that the filter itself is represented or governed by this transfer function h of s, the overall behavior of this filter, whether this filter is going to behave like a low pass filter or a high pass filter or a band pass filter or a band stop filter, will be established by adjusting the coefficients a0, a1 and a2 in the numerator polynomial. So this statement is super important, that the overall filter's behavior will be determined by the coefficients, by adjusting the coefficients. So this is what I'm going to discuss now in a tabular format. Alright, now let's consider some special cases. What I want you to do here is, as I mentioned, we should tweak the values of these coefficients a0, a1 and a2 to get desired type of filter. For example, if you wish to make a low pass filter, we can keep the values of a1 and a2 to be 0. Now keeping a1 and a2 to be 0 will give me my transfer function to be equivalent to a0 upon b2s square plus b1s plus b0. Now if you look at smaller or zero frequency, or at the lower end of the spectrum, you'll find that this approximation will lead you to a conclusion that the transfer function is a0 upon b0, which is constant. So at lower frequencies, the two-port network will behave like a low-pass filter, and at higher frequencies the transfer function says that it is inversely proportional to the frequency. The attenuation will be larger, so this will act like a low-pass filter. So if in the transfer function of the filter I make a1 and a0 to be 0, then my transfer function becomes a2s square upon b2s square plus b1s plus b0. Now if you look at this approximation now, where at s is equal to j omega is equal to 0, my transfer function reduces to 0. So at lower frequencies the signal is not being passed, but at higher frequencies it will have a constant value with which it will be passed. So if we make a1 is equal to 0, we get h of s to be equivalent to a2s square plus a0 upon b2s square plus b1s plus b0, and it gives me the characteristics of a band. This will give me the characteristics of a band stop filter, and a band pass filter can be made by making a2 and a0 to be equivalent to 0. So that will give me a1s upon b2s square plus b1s plus b0. But the concept here is to understand the idea behind tweaking the values of the coefficients in the numerator, so that when the approximations are made, they'll give us the response of this two-port network, which is our filter, to be closely matching either of the types. It could be a low pass filter, high pass filter, band pass filter, or a band stop filter. But as you can see, we are talking in terms of frequency, we are talking in terms of the transfer function, so the calculations are more accurate, the designing is more accurate, and the inculcation of op amps and capacitor excluding the inductor will make the design even more interesting. So I hope this introductory session on active filter design was of help, and you're intrigued by the way they are going to behave. So we'll talk more about these filters in the coming tutorials. Thank you for watching the video. Take care. Bye bye.